Really good how that works, isn't it? Good morning, all. Thank you. We've still got one speaker coming, hopefully, with any luck. Thanks all for coming to this session entitled Navigating Naturals. My co-chair, Sían. We practiced that and I still got it wrong. And I will be chairing the session. Okay, our speakers have arrived. Excellent, thank you very much. Fortunately, we've got some instructions we need to read out. If we had to remember them, there might be problems. First one here is you can drop any luggage tomorrow at the Edge Hub, which is opposite Connections Live Brick Building. Oh, where we are now. Yeah, okay. So I don't know where the hub would be. Is that?
It's across the road.
Okay, so everyone got that? It's the place across the road. There'll be a 2-minute AORG presentations taking place, which you can see in the program. We've got 3 talks today, questions and answers. Full speaker biographies are available in the conference app, and we'll just read out a short abridged version. Questions and answers, you can ask questions through the session, through the conference app, under the agenda, and then click onto the conference session. So you'll be monitoring that through that. Thank you. Fire alarm. I think we said this morning there's no planned fire drill, so if it goes off, it's real. The best exhibitor award. Please make sure that you vote for this by 12:30 or 13:20 on the conference app. Annual dinner. If you're booked onto the annual dinner and not placed on a table, please make sure you do that through your table, through the conference app. If you have any problems doing this, please visit the conference app help desk located in the exhibition hall. If you can no longer attend, please let the conference organisers know, and you need to do that by 1:20 or 13:20 today. So our job is to keep the speakers on time, and we'll do that viciously. And over to you.
Right, so there's also some posters related to this session. So these are poster 12, large-scale assessment of radon exposure in private dental practices across the UK and Ireland by Dave Hughes and Scott Grieve. We've got poster 13, assessment and comparison of the long-term performance of electronic radon integrated monitors by David Wright. Poster 14, radiation hazard assessment of non-waste produced by crude oil refinery using gamma spec by Ikra Zamir. And also poster 15, measurement of naturally occurring radioactive materials for some granite rock samples in the northwest region of Pakistan by Hannah Yonis. So these can be found in the exhibition hall downstairs where you've been at the back end. Cool.
Thank you. So we'll move to our first speaker, Karishma Patel. Welcome. Karishma's job is as a health physicist with DRPS, involves carrying out RPA visits to armed forces locations to advise customers on compliance with legislation and defence-specific policy, delivering radiation protection training to customers at sites across the UK, supporting carrying out environmental surveys and contamination monitoring, and supporting the Radiological and Nuclear Emergency Response Organisation through her role as part of the Nuclear Emergency Monitoring Team. Now, this is Karishma's first conference, so please welcome her, and over to you. Thank you.
Hi everyone, welcome. Thank you for making my first conference experience a memorable one. So as the chair very nicely said, I work with Defence Radiation Protection Services. We're part of AWE and we are the RPA to the Ministry of Defence. So this is a project that I've sort of been working on alongside our training scheme, which I recently qualified from, and it's twofold. We're looking at the effect of sealing radium items and also the RP implications of that in terms of contamination control. And then the second phase is sort of looking at the the impact that that has on potential radon off-gassing and off-gassing of radon daughters. So to start with, a brief overview of radium for those of you that might not be familiar with the isotope. So we've got a diagram of the decay chain here. Main things that I want to highlight here is that radium-226 is a bit of a triple threat because it emits alpha, beta, and gamma radiation. It has, in the context for which we're using it and for the items that it's used on, it's got a relatively long half-life of around 1600 years. Its decay chain includes radon-222, which, spoiler alert, we will come on to a bit later in the presentation. So we're concerned in terms of hazards and route and intake, obviously, because it emits all three, alpha, beta, gamma. It's both an internal and an external hazard. So the main issue we're concerned with for your internal hazard is your alpha. In terms of routes of intake, we're looking at inhalation. So if you've got loose contamination on surfaces, and then you get a resuspension, you potentially breathe particulates in, and that results in internalization of the radioactive material. We're also looking at ingestion. So that's a case of if you've got sort of poor RP controls and general health and safety. So you've got contaminated surfaces, and then, you're handling items, you don't necessarily wash your hands, and then you get that internalization of radioactive material again. And for injection, not really looking at a syringe full of radioactive solution or radioisotope. In this case, it's more if you're handling items and not in great condition, any breakages, or, if they're damaged and you get a cut or a wound or an abrasion, that's also another route of intake to get it inside you. And obviously then the external hazard is your dose rate, and that's mainly your gamma and your strong beta components. So in terms of historic uses, so radium was discovered in 1898 by Marie and Pierre Curie, and it shot to popularity in the 20s because it was hailed as this miracle, wondrous substance that supposedly has lots of restorative and regenerative and curative powers. So some of you may be familiar with the term radioactive quackery, and this is basically where they discovered radium and they decided this is the best thing ever, and they just decided to put it in everything. So creams, tonics, potions, suppositories, you name it, probably had radium in it if it was the 20s. Obviously, at the time, this was because they weren't aware of any of the negative side effects in terms of like the health implications and the impact of overexposure of radiation. That came on a lot later, which is probably why it's no longer used today. So in terms of military, because obviously we work with the Ministry of Defence, so for military applications, the main use was sort of in radioluminescent paint. So radium's really good because it can be mixed with a phosphor, and in this case, I think popular one around the time was zinc sulfate, and that is effectively where you'll have the alpha emissions from the radium interact with the phosphor in the paint, and it causes it to glow in the dark. So this was great because then you'd mix it in with paint, and you could apply it to anything effectively that you wanted to be able to see at nighttime. So in terms of military applications, this is stuff like compasses, watches, gauges, dials, an aircraft, vehicle, or anything that you might carry on your person that you'd want to be able to see. And because of its long half-life of 1600 years, it's going to glow in the dark pretty much for as long as you need it to. This was pretty much used up until the 60s, and then this is sort of the time where they realized that, oh, actually, this stuff's pretty bad for you, and it results in some really, really nasty health effects. And a key one of these cases that led to this discovery was the case of the radium girls. Some of you might be familiar with this. There's been many documentaries made on them, and these were the women that used to work in the factories where all of these items and artifacts were made, and they would all be hand painted with the radium paint. And a lot of the time what they used to do was they'd lick the paintbrush in between applications to get that really fine point on the tip for the fine painting work. Obviously that led to a massive intake of radium, and over time, if you think they'd be working in these places for hours a day, multiple days a week, many weeks a year, that over time resulted in a really, really huge buildup and a massive internal dose. And, they ended up with some really, really nasty side effects. They developed cancers, sarcomas, tumors, and unfortunately, a lot of them did die from this. It was actually quite a good basis for the lessons learned in terms of this is a lot of the underpinning principles that were then used going forward for other health and safety legislation that we have today. So, for example, management of health and safety at work regs are in place to make sure that employers are not only doing something to protect themselves from the hazards associated with radiation, but also that they're protecting their employees. So key thing with the artifacts that we deal with in our work is that even though they no longer glow in the dark, because radium has a very long half-life, obviously they're still just as radioactive as pretty much the day that they were made. So here I have a picture of a common type of exhibit that we might find on our travels when we travel to all our different military sites to visit our customers. This is a display case in a heritage centre at RAF Leeming, and as you can see, it's got 5 items in there, all of which contain radium paint. So again, this is something quite common. These are the type of artifacts we'll find. And to give you a little bit more context, these are some images of some of the things that we find and some of the items that are held by a lot of our customers. It varies across the different services. You'll find some of them. So for example, RAF, they have a lot of compasses. There'll be things from that quite common, like aircraft gauges, compasses, etc. And then some more unusual pieces like the theodolite, which is used in cartography and survey work. The key thing to note here is sort of, you can sort of tell it's radium paint, mainly by the sort of off-whitish, orangey brown colour of the paint. Obviously, when it was fresh paint, it would have been nice bright white. Over time, it's obviously degraded, and it's that sort of off-white rust colour, which is very key indication when we look at these things that are that, along with the age of the item, we can pretty much say that's probably radium. Obviously, we can't confirm this without using a survey instrument, and then we'll just confirm that yes, it is radium, because sometimes, very rarely, we do find things that look like they're radium and maybe they're not, but generally the colour of the paint and the age of the item is a good key indicator. So what is the problem with having these items that have radium paint on them? So from an RP point of view, the main thing that we're considered about is obviously the potential for contamination. So a lot of these things are not necessarily in good condition. They may be rusting, they may be flaking paint, and then that's obviously a contamination risk. Now, it's not always obvious. Obviously, some of these items could look like they're in fairly good nick, they're in good condition, they're not like any obvious chipped paint or anything, but that's not to say that the surfaces that it's stored on or the area that it's displayed in is free of contamination. Again, just to highlight that alpha is the main thing that we're concerned about here in terms of the internal hazard. So when you think, right, you've got all these old collection of items, and they contain radium, some of them might be unsealed, well, the logical solution would be to get rid of them, because if you remove the source of radiation, then you don't have to worry about contamination. However, a lot of the places that we work with, obviously, they have historical significance within the military. So to give you an example, these are just some of the things as part of collections that our customers have. They range, they can be individual items or, such as watches and presentation clocks. The whole point of museums and heritage centres is to preserve that history and, make sure you're keeping that heritage. So they do like to keep things like these that are historically significant, and not necessarily on a national scale, but even if it's just historically significant to that particular unit or regiment, that's something that they'll want to keep hold of. And they can vary in size from individual items, as I said, to whole displays where you'll have multiple dials and gauges. So we've got a picture of the inside of a cockpit of a display aircraft at the Fleet Air Arm Museum in Yeovilton, and that's got a number of dials on display. It's not just individual things. Sometimes they can be a little bit bigger. So this is a picture of a Sherman artillery piece at the Royal Artillery Museum. Now, this has a panel inside of it, which has lots of radium gauges on it. Obviously, there's no external dose rate from this outside, so if you're walking around the exhibit, you're fine. But if for whatever reason you have any employees of the museum that need to enter the tank for whatever reason, for example, to carry out the 2-yearly leak testing on the radium gauges, then that would be the contamination risk that we'd be concerned of there. Also, as a minor spoiler, you'd also be concerned with radon, because obviously it's an enclosed space. So that's, in that sort of case, you would have work instructions in place that basically say, if you did need to enter the vehicle for whatever reason, you have to ventilate it to allow the radon to dissipate, that kind of thing. And then this is one of my favourite pictures, actually, on the other side. For those of you that are not aware, this is a picture of the Dakota aircraft at the Battle of Britain Memorial Flight, based at RAF Coningsby. They have a collection of authentic historic aircraft, mostly World War II era, and they're all original working parts. They're flight worthy. This is a really good example of sort of like why it's important to maintain that authenticity and heritage, because some of these are one of very few in the world. For example, they've got a Lancaster bomber there, and to give you some context, unfortunately I wasn't able to find a picture of that, so I've got a picture of the Dakota, but the Lancaster bomber is actually one of only 2 flight worthy of its kind in the entire world. We have one at the Battle of the Britain Memorial site, and the other one is owned by the Canadians, and that's it. They're the only 2 working aircraft we have. So it's really just important to preserve that heritage, to make sure that we've got all the authentic and original parts. So if you can see in the cockpit picture at the bottom there, it's got multiple dials, gauges, toggle switches, all sorts that have radium paint on them, so they're unsealed sources. Some of these can be quite pokey. So again, we're worried over time, degradation of the paint, potentially flaking off. People are in and out of these cockpits all the time, just for practice of flight hours, etc., maintenance. So that's something that we're quite concerned of. So we have these items that have historical significance. So what is the solution? What can we offer our customers to deal with this? So currently we have 3 options available, and have been provided some photographs very kindly by my colleague Steve Kane in DLPS, who's part of the survey team. And generally we say to the customers, well, we can either remove the part of the item that contains the radioactive material. So at the top there, we've got a picture of a weapon foresight that has a dot of radium paint on it, and that has been removed using a V-cut, and effectively that then little blob of metal with radium paint will then be transferred for disposal as radioactive waste, and it allows the museum to keep the rest of the weapon on display and not have to worry about having a source of radiation. The other option that we have is we can permanently encase it. So this is, I think, a very interesting example. It's a pocket watch owned by a lieutenant that actually, when it was hit by a bullet, saved his life, because the bullet hit the pocket watch instead of him, and he lived. So obviously the museum would want to keep that because it's quite a significant piece. You can see, it's not clear on the photo, but the numbers are radium paint, and where the bullet has hit, any of the shrapnel from the face has actually fused to the remains of the bullet. So in that case, you couldn't really remove the bits of radium without defacing the object. So what we did in this case was we permanently encased it in an acrylic box, and then that way the museum can keep the piece, not have to worry about any degradation and can result in contamination over time, and they can just then put that box on display, and there's no risk of contamination. The other option we have is obviously they can get rid of the item, legally, of course, following all the legislative requirements. And that's basically where we say, if you don't have use of it and you're not going to display it, then you can get rid of it. So we transfer it to Central Stores, which is at a site in Mod Donington, and then it gets given over to a radioactive waste contractor for disposal. So these options aren't a one-size-fits-all. So for example, if we go back to the aircraft that they have at BBMF, they can't really remove the part of the item that contains the radioactive source, because you'd end up taking out half of the dashboard and the aircraft. You can't really encase it because, again, it's a working aircraft, so you need to be able to use it, and you can't get rid of the item because we really want to preserve that authenticity and the heritage represented by those pieces. So we've come up with a potentially new cure, and this is to seal the exposed source, so permanently seal it using a UV cured resin gel. So how about sealing it? This is the definition of a sealed source. Now, conventionally in the past, normally for things that have exposed radium paint, you could look at potentially using a lacquer. The issue with using a lacquer is obviously degrades over time. If the lacquer then starts to flake off, then you've got the same contamination issue. You've got contaminated lacquer. So that's something that we want to avoid. In this case, we're using a UV cured gel, so it's a thick viscous gel. It goes on over the radium paint. We then UV cure it, and it's pretty much set. That's now a permanent seal over the open radium paint. That's not going to come off over time. So in that sense, we're removing the risk of contamination from the flaking lacquer. So would this work? Obviously, we didn't want to whack it straight onto all these historic artifacts without trying it out first. So we did a few trial runs, and basically we picked a bit of metal pipe that was sort of representative of the materials and the type of items we'd be sealing. A lot of the things are metal and glass. And then we did different layers, and then we did a strength test, which was effectively whacking it really hard against the surface to see if it splintered or cracked or chipped off, and it didn't, so we were happy with that. We also did multiple layers and different orientations, because obviously on a flat surface that works, it's great, but not all of these items are flat surfaces that we're going to be sealing, so we wanted to then try it in different orientations for different items. We also tried 2 layers of resin as well, just to double check that it's not just going to pop off the end, and if it has 2 layers it still seals properly and it's still a permanent seal. So that was all successful. So did it work in the end? These are some pictures of some items that we sealed at the Fleet Air Arm Museum in Yeovilton. So the curator very kindly gave us permission to try out this technique on some of the items that are in situ in their aircrafts on display. So the circles highlighted all the bits that we sealed with gel, and luckily you can't really tell that they've been sealed with gel, which is good because it doesn't deface the object. I'm going to caveat this by saying, obviously, this is a new technique that we're trying out. We don't know what happens long term in terms of the effects of the resin over time. And this is something that we do make clear to our customers. Obviously, we advise them on all their options. We tell them all the risks, tell them all the benefits, give them their options, and then they will normally take that to their board of trustees or their executives or the head of establishment, and they'll basically sign off to say, yes, we're happy to go ahead with this, and then we'll seal it. So obviously, these are subject to two yearly leak testing, because they're radium items, so they're leak tested every 2 years. When we do the sealing originally, we will do a smear to probe there and then once we seal it, just to double check that the seal's fine, and that we're happy and it's not leaking. Obviously, if it comes back as false positive, we might potentially do a second layer of resin, or even for aesthetic reasons, if the museum decides that, oh, actually that looks a little bit messy, we'll just want a second layer of resin, we'll do that, and we'll do a smear to probe using an alpha contamination probe to double check that we're happy. It's then leak tested every 2 years, and obviously the curators do visual inspection regularly of it, and they will let us know if they notice any occlusions or anything wrong with this resin over time. These items were all sealed back in 2022. So far, all of their leak tests have passed, and we've not had any issues. The curator's happy with how they look and their condition. So far, it's looking very good. So we're happy to say that so far the tests that we've done on the resin sealing look positive, and we've not had any issues with them. So now, obviously, that's the first phase of the investigation. Next, we want to look at radon, because that's also an issue when we're considering radium items. So what about radon? Just a very quick whistle-stop tour of radon. Obviously, it's a direct decay product of radium-226. Got a half-life of about 4 days. Now, the radon itself decays eventually into stable lead-206, but the issue is it has a lot of short-lived chemically reactive daughter products along the way that are listed in the table there, and those are very chemically reactive. So obviously if you inhale them, they get into your lungs. Your lungs have very radiosensitive tissues, so we want to avoid that as much as we can. Radon's naturally occurring as it is anyway, but what we're looking at in particular is we want to look at the impact of the seal, if there is one, on the off-gassing of radon and the off-gassing of the daughter products, the release effectively from items that we've resin sealed. So does the seal effectively cap all the products and not let it escape, or does it still let it off-gas as normal? So how would we look at this? Obviously, passive radon detection is you put a detector in place, it sits there for a couple of months, you then collect the data from it and do a time average seasonally corrected radon dose for the room that you've measured. That's not great for looking at a before or after of a specific item. So we decided the experiment that we were designed to look at this would be gamma spectroscopy. So we used a portable Ortec Detective X, and we basically took a gamma spec of items that we wanted to be sealed. So these are some items at the Rifleman's Museum in Winchester that the curator wanted to have sealed. What we did was we thought, right, we'll take a background of the room, because obviously the detective instrument is very sensitive. Took a background, we then took a spectrum of each item before sealing, each item immediately after sealing, and then each item 4 hours after sealing. So it would kind of be a little bit of a litmus test and indication to see if there was going to be any change in the off-gassing of the radon and the radon daughters. We did this by using peak identification and comparing the spectra. So we used the radium-226 peak, the lead-214 peak, and the bismuth-214 peak, and basically compared the ratios of them across the different spectra. Obviously, this was an initial experiment. We mainly wanted to look at what we could learn from it and what we could do better next time. So we weren't expecting to get any conclusive evidence from this, because we also only had 2 data points. Initially, we didn't see any change, but like I said, it was mainly about the lessons learned. First and foremost, looking at the sensitivity of the gamma spec. So having some sort of jig to make sure that we can replicate the measurements, because orientation will definitely affect the spectra that you get. We also want to look at potential control items in comparison, because we don't have any data on just spectra of radium items over time. So I think it would be good to have a look at that just to sort of compare. And also other environmental conditions. So for example, temperature, humidity, ventilation, are people moving through the area, because that's all going to have an effect on the radon concentration in the background anyway, and also the measurements that we take. So What next? Obviously, first and foremost, we want to get more data. So we've got a plan in place to do 6 to 8 monthly monitoring of these items that we've sealed. So we're going to go back, redo the spectra. We also then want to have a look if potentially the seal does cap in radon and radon daughters, is this going to contribute to the dose rate? Storage and display implications, obviously it's optically cured gel. It cures over blue light and UVA, but are the different lighting that might be on these exhibits after they've been sealed, is that going to affect the integrity of the seal? And also other factors as a human factors element to consider, because the gel is applied by a human, so no two applications are going to be the same. First and foremost, we do want to look at the changes over time. So obviously long-term effects, 10 years, 20 years down the line, what's going to happen to these, what condition are they going to be on? So to bring it back, finally, is sealing the cure? I think potentially it could be. I know it's a very political answer, but yes, it could be. I think based on the data and the research that we've done so far, it's a really great way to deal with the contamination issue that is presented by some of these unsealed radium items. In terms of its effect on radon, that's obviously very much an ongoing project at the minute, and we've got plans to expand and look at lots of different avenues. So watch this space, I would say, and hopefully I will be back in a few years with an update for you all potentially. So thank you very much. Finally, just a huge thank you to everybody who helped make this project possible, and to the curators at the museums, without which this project would not have been possible. So thank you very much.
Thank you, Karishma, and excellent first presentation.
Thank you.
I think you did very, very well. So thank you for that. So we now have a presentation from one of the sponsors, Phoenix Dosimetry.
That's correct. Yep. Mike Sweeney.
Okay.
Yep.
I'm introducing Mike Sweeney.
Right. Well, that was a great talk, Karishma, by the way. Very good. Very well presented. My name is Mike Sweeney. Welcome to Hull, everybody. I'm from Phoenix Dosimetry, and I'm just going to spend 2 minutes now telling you a little bit about our company and some of the products. So we're based in Sandhurst since 2013. And just over a year and a half ago, we became part of the HGSL group. So you'll see our stand downstairs, basically. We distribute for several companies, including Thermo Fisher Scientific. And basically, a few products we've got. You're probably aware that Thermo stopped making the mini instrument products about 2 years ago. And we've now introduced the mini handle, which takes the old mini probes and combines it with the Radii SX and GX units. So it's a very, very good way of using the old probes, etc. And it means you can use it either single-handed or take the probe out as well for survey work. In terms of the Radis, we've got the Radii B20, probably our most popular Radii. The B20 is both a contamination dosimeter, it's a Geiger looking at alpha, beta, gamma. But if you fit a filter on it, either a H-star 10 filter or a HP 0.07 filter, it then automatically converts to a dose rate meter. So it's a very, very powerful instrument, sold a lot in nuclear medicine type departments, but a very, very versatile unit. We've also got some quite new innovative products, and we've got a combination of Polymaster, and you'll see the Polymaster stand downstairs. Polymaster make a very nice dosimeter called the Rad Flash, and in combination with Charthouse, who make a terminal, this links Bluetooth in a seamless way with Bluetooth, basically. So people in things like interventional radiology can be wearing dosimeters and have up to, say, 10 or 20 dosimeters. And on a large HDMI monitor in the room, you can see instantaneously the dose and dose rates, basically, so they can monitor very, very quickly. The Rad Flash uses a Geiger, but the transmission time is very fast, less than 1 second. So you get instantaneous dose appearing on the screen, basically. So if you want to have a look at that further, go to the Charthouse stand downstairs. We're also involved in radon monitoring. So we represent Femtotech. This is a very, very sensitive pulsed ion chamber device that can be deployed for doing survey of radon. Very, very popular. Again, it's downstairs in our stand. A new product that we've launched about a year ago were radioactive wipes. So this is quite innovative. These are wipes. So a company called Kodiak developed these, and they're just about to launch a new version of it, which is about 1,000 times more sensitive to the old version. And the idea is you have a wet wipe or a dry wipe, you wipe a surface, and within 1 minute it will change color if it detects certain isotopes, basically. So it's a very, very powerful way of doing screening. And very innovative. There's very few innovations really technically in this field over the last 20 years, and say this is one of the big innovations. In terms of other monitoring, we do tritium monitors with Femtotech. We've got a small chip reader for deploying, which uses OSL chips for doing small departments, say radiotherapy departments, looking at patient doses, for example. And then finally, just showing you again the Rad Flash device, very powerful. It's got its own app software on the iPhone or Android, so you can actually link wirelessly to it, reset the doses, set the dose and dose rate alarms. Very, very versatile device. And also on the Polymaster stand, you'll also see they've got a very, very nice handheld RID, which is used for identifying isotopes. Got 2 detectors in it, got a Geiger and a scintillator, and it can do alpha, beta, gamma, and give you spectrum analysis. That's my 2 minutes over, so thanks for listening. Okay, take care. Cheers.
Thank you, Mike. And I encourage everyone to visit the stand, and great presentation. Our next speaker is Zornitza Daraktchieva. Did I get that right?
Yeah.
Thank you very much.
Zori.
Zori, yes, that's right. So Zori is a team leader on radon dosimetry in the UK Health Security Agency. She's a physicist with extensive experience in radiation modelling and energy calibration of particle and nuclear physics detectors, Monte Carlo simulation and statistical analyses. And you are going to be speaking to us about how to use the consumer-grade electronic integration radon monitors for reliable results. Over to you. Thank you.
Okay, I'll cover the kind of new instruments on the market. For about 10 years, the market was flooded with these new electronic radon monitors. We call them integrated because they can provide integrated results. So we call them ERIM for shorter. They're consumer grade, which means that they can be bought by anybody. There are probably millions sold already. And yes, we started exploring them and study them about 10 years ago. It was a little bit slowed down because of COVID. So I'll just present a few of the things. So the outline is radon fundamentals. I will not cover much because it was already covered. Yesterday, the lecture was extensive about the subject, but a little bit. And also measuring radon, the most important methods, and ERIM itself to present some misconception about their usage and how to use them reliably. Okay, so I'll skip this. You already heard about radon. I'll say why we're interested, because I'm sure that all of you know that it's the second greatest cause of lung cancer, and actually it's responsible for the single biggest source of radiation exposure for the UK population, about 48%. Okay, radon is everywhere on Earth. You cannot go on a place that there is no radon. And importantly, how does radon get into houses or buildings? There is a little bit of under pressure caused by the temperature difference between indoors and outdoors. Small temperature difference causing this small under pressure, which drives the soil gas, and soil gas contains radon. It's a very simple mechanism. What's not simple, because radon is a gas. And first, there are several sources of radon. The most important one is the soil being the building, but could be radon from, let's say, water supply or gas supply, building materials, and outdoor air also. And this is started to be a little more complicated. So we started with the radium content of the soil, but then you have to add to this permeability of the ground, then entry routes of the ground, then occupational pattern and usage of the building, and then ventilation rates. So all this is kind of multi-parameter equation on the top of this, because radon is a gas. It depends on a lot of environmental parameters. I said outdoor temperature, pressure, wind direction, and strength, and rainfall. Everything's, if you had everything, it is quite very difficult equation to solve. Some people tried in Europe to model indoor radon. In my opinion, it's impossible. I'm a physicist, and I don't believe that you can model radon because of every parameter varies differently. And the only stable one is radium content of the soil. So you can see how radon varies. This is the real measurements in a school. Daily variations from below 100 to a few thousand. So it's very, very variable. That's why we're measuring long-term radon. We're interested in long-term measurements. This is the probably the one that is kind of known to you by passive methods of passive radon detectors. This one actually is the H-track detector, because there are other passive radon detectors. What what it has. I'm not so sure. Is there any kind of the pointer or how to use the pointer? No. Okay, it's fine. Okay, on the right hand side, you can see the detector. The detector is the plastic, so-called PADC plastic, very simple one, invented during Second World War, and it was in use until these days. Why? Because it's very simple. Actually, it's not very simple to produce the detectors, to maintain the quality, but it is kind of easy. It's easy to use. This plastic on the right-hand side is enclosed in the plastic holder, which is on the left-hand side. And there is a small gap through which radon diffuse. When radon diffuse and decay, it produces, obviously, the decay products. And all of the alpha emitters of these decay products can produce a track on the plastic. This track is invisible until it's etched. That's why it's called the etch track detector. And these small dots that probably you can see, hopefully you can see, each one of these dots is produced by one alpha decay. So yeah, this is one of the methods that we are measuring radon, and we're producing passive radon detectors in our lab. Another method is through continuous radon monitors. These are, I think, more popular. Most of you know about them. AlphaGuard, Atmos, RAD7, they can operate in passive diffusion and active mode. They require power supply. They have fast response time. They're suitable for short or long-term measurements, but they're quite expensive. And this is the problem. Why is a problem? Because people would like to buy instruments a little bit cheaper and yeah, a few other things. So the market was flooded with so-called electronic radon integrated monitors. We, as I said, call them IRIM for shorter. Some people call them a little bit differently, but it is our abbreviation. There are 3 generations of IRIM. The first generation was Raman. I think Raman was the first of this kind of models, but it wasn't very popular. So Raman and Canary, now it's called Corentium Home, they're the first generation. So what you can do, you can see the radon on the screen, and you can see only the integrated result. The second generation was the instruments like Alpha E, AR Plus, Radon Scout Home, and so you can download the data through application. You can read something on the screen, but it's not what you can have. And the third generation, which is the most attractive, but also more problematic, it is like Radon Eye, View Radon, Spirit, and EcoCube. So you can have the application on your phone. You can constantly see the radon values. So you're happy. What you see is what you get. Is it? Well, the main features of IRIM, as I said, they have electronic components that require electricity to operate. They operate in passive diffusion mode, which means that air is diffused into a volume. They provide integrated radon measurements. Some can provide also time resolved measurements. I mentioned that they're very popular because they're cheaper. And also they can display radon concentration on the screen. So people are happy. Okay, these are my radon levels. So I can see what I have. They're advertised, moreover, as self-calibrated or calibration not required. And they're advertised as a replacement for passive detectors. Some can provide, as I said, time resolved measurements. So they're kind of a good replacement for more expensive instruments. So AlphaGuard is about 12,000, and IRIM can be up to 500, let's say up to 1,000. Obviously, it's attractive. What we did, because we had a lot of inquiries from customers, from colleagues, so we decided to study these instruments. For the study, we used our UKHSA radon chamber, a radiation calibration facility. Our radon chamber has a volume of 43 cubic meters. It's the second largest in the world. Until recently, it was the largest one, but now there is one that is larger than ours. And radon is produced, and there is a steady state in constant emanation type. There are 4 dry radium sources. And radon concentration can be changed between 400, I can say 300 because we 300 to 8,000 becquerels per cubic meters. And we can also change the equilibrium factor from 0.1 until 1. Yes, so we monitor constantly radon concentration with two sources, two instruments, Atmos and AlphaGuard. And these two instruments are annually calibrated against the primary radon standard. It's not easy these days to obtain primary gas radon standard. There are only one laboratory in Europe, in France, which we use, LNHB France. There is one in US. So there are very limited choice of labs. NPL closed long ago the production of radon sources, and PTB in Germany also don't produce anymore radon gas sources. So our instruments actually are the secondary standard. What are the common misconceptions about helium? Okay, first, they don't need calibration. I'll tackle all of these misconceptions. They can provide fast measurements. One monitor can be used in many rooms, and they can replace passive radon detectors. First one, helium don't need calibration. On the picture, you can see 4 canarium or corentium home instruments. So the monitor, these monitors in the UKHSA chamber, they show radon concentration between 8,700 and 8,950. But the reference radon concentration in the chamber was 4,880 becquerels per cubic meter. So is this really the case that these instruments can show radon concentration without calibration? So we studied the calibration factors of 27 instruments. We bought them as part of the project, and we individually calibrated them using our radon chamber, UKHSA radon chamber, and compared the values of calibration factor in March 2019 and then in August 2023. The calibration is just, it is not routine calibration because these instruments, I'll show you later on, don't have fast response time. Some of them required up to 2 days just to show any result. So what we are doing, we are placing them in a chamber with 0 radon or in nitrogen for 1 week. And then in 1 week, we're placing instruments in the radon chamber to high radon concentration. And we calculate the calibration factor, which is the instrument, what the instrument is showing as radon concentration minus the background divided by the reference concentration. So you can see, hopefully, in the table, the changes in the calibration factor. We also calculated the percentage change of these calibration factors. And on the plot, you can see probably a little bit better. What we found that some instruments changed the calibration factor by 60%, plus 60%, some minus 50%. There are a few instruments that were quite stable. They didn't change much the calibration factor, such as Ramon's, Alfie, and Radium Scout Home. But some changed significantly their calibration factor. The results are published there, so if you're interested. Okay, so what we can say, calibration is important because it can provide a way to calculate meaningful results. And if something happens with your instrument, the calibration factor will be the first just to indicate this. The second claim about helium was that they can provide fast measurements. So we studied the response time. How we studied the response time? Instruments were left in the nitrogen cabinet 0 radon concentration for about several days, and then they were moved faster into the radon chamber with radon concentrations between 4,000 and 6,000 becquerels per cubic meters. So what you can see in the plot with red is the reference radon concentration in the chamber, and with dark blue is the response of two instruments. On the left-hand side is AR+, on the right-hand side is Corentium Pro. So the response time is the time required by instruments to reach the reference instrument at 90% of the reference random concentration. And the 90% response time was achieved for AR plus for 80 minutes. However, for Corentium Pro, it was achieved for about 4 hours. And we found another instrument, Wave, that achieved this in 14 hours. So yes, some instruments can provide fast measurements, but not all. Another misconception, one monitor can be used for many rooms. Yes, this is true. However, before starting a new measurement, the monitor needs to be reset. It needs time to adjust to the new concentration, bear in mind here the response time. It needs to be left undisturbed in the place and not move from period of the measurement. If these are not actually met, the average result will include the random concentration in all monitoring rooms. This is especially true for Ramon and Canaries. The Canary is one of the most popular now. It's called Corentium Home anyway. Another one is that IRIM can replace passive radon detectors. Again, it is true if they are placed according to the following instructions for passive radon detectors. UK requirement just to leave passive detectors, in this case IRIM, in position for about 3 months. Do not move the detectors during the measurement. At the end, record, download, acquire the data, calculate radon concentration, and apply the calibration factor. And also in UK, we have validation scheme. For validated laboratories, they need to use the seasonal correction factor because we're measuring only for 3 months. You have to extend this to a whole year. And also occupancy factors. Okay, just to summarize how to use IRIM for reliable results. You have to take great care of choosing your instrument that is appropriate for what you'd like to use it. Check if your monitor is calibrated and not the calibration factor. Read the manufacturer instructions. You have to change the batteries. You have to reset the instrument. You have to make sure that the internal clock matches the clock, because otherwise you have some data that cannot be matched to any meaningful time. Then you have to leave the instrument undisturbed. At the end, just calculate the integrated result or not the integrated results, apply the calibration factor. And sounds simple, isn't it? And for those of you that will be using these instruments for workplaces, obviously they have to comply with RRR 17. And there is a proof code of practice guidance 23 that requires annual calibration and proper maintenance of these instruments. And I would like to thank you for your attention.
Thank you, Zoe, for a very practical presentation on how to measure radon. So great presentation. Thank you very much. Next on our agenda is a presentation from
Cerberus Nuclear.
Yeah, your name.
Oh, me.
Yeah.
Zach.
Right. Zach from Cerberus Nuclear. Thank you.
Hello, I'm Zach from Cerberus Nuclear. I'm a radiation shielding assessor. We're currently exhibiting downstairs. We're at stand 25. If the lunch rush is anything like yesterday, you'll nicely find us situated at the back of the queue, so you can spend plenty of time enjoying our stand. We are a small technical consultancy. We're based in Birchwood Park in Warrington. And yeah, there's between 20 and 30 of us in the company. We're very small, but we're growing quickly. We have 3 main specialisms, really. It's radiation shielding. We do Monte Carlo assessments, different types of computer modeling, really, all across the shielding design process. So basis of design, shielding assessments, dose assessments, the whole shebang. Yeah, and we have a team of criticality safety experts. I think we technically have the largest dedicated criticality safety team in the UK, even though we've only got like 30 people in the company. there's a big need for crit assessors. And nuclear characterization, we do a lot of stuff with data science and done a few of the Game Changers projects through Sellafield, if anyone's familiar with those. And we do a lot of innovation work in the nuclear industry with AI and various stuff like that. Today, well, for these 3 days we're exhibiting, we're demoing 2 of our products. The first one is Carter. It's a criticality safety training tool. And the idea is training glove box operators, they can't make a criticality happen in real life. So a lot of the training goes through slog of slides and just learning all of the background content, and it's a bit dull. So we've got this VR tool where you basically simulate glove box operation, and it's a handy training tool where you can see what changing the different factors that affect criticality. You can mess around with it, cause a criticality, and it won't be an international disaster. So yeah, we've got that demo in downstairs. We've got a non-VR version that you can access on our website. But if you want to play around with some VR, we've got that downstairs. And the other thing we're demoing is Cyclone. It's an MCMP visualization tool. You can do all sorts of 3D visualization. It's really handy for communicating dose rate contours, that kind of thing. But yeah, as I said, we're demoing everything downstairs. So if you've got any questions or anything, come and see us. But yeah, I won't take up much of your time. That was everything. Thank you very much.
Thank you very much. So our next speaker up is Dr. Nicole Martinez. Nicole is an associate professor in the Department of Environmental Engineering and Earth Sciences at Clemson University, and also holds a joint faculty appointment at Oak Ridge National Laboratory within the Center for Radiation Protection Knowledge. She's going to be talking to us about application of modern dosimetric methods to the American radium dial workers.
Great. Thank you so much. Just lower these for me. I almost need a little box to stand on. Well, Karishma's presentation, excellent presentation, has set me up very nicely to talk about the American dial workers, where American is the US, as you might guess from my accent, or not accent to my ears. To start, I did want to acknowledge that we wouldn't be able to do this work related to the dial painters if the scientists before us hadn't been vigilant in preserving their records. The last follow-up of the dial painters in the United States was in the early 1990s, when the program was rather unceremoniously canceled, and the scientists could have just been like, oh, well, trash. And they didn't. They retained it, involving, I forget who it was, but someone loaded up, we couldn't do this now, their personally operated vehicle with all the samples and paperwork, and drove it to the University of Wisconsin, of Washington, where a lot of those tissues and records still are. Like, they could have shredded those records and they retained it. So we're really indebted to all those workers. Since I have a little bit of extra time, so I don't have to tell you all the details about the dial painters, I will tell you a fun story about Robley Evans. Robley Evans, bottom, middle, left, right. So this is him. He's at the Massachusetts Institute of Technology, one of our American radiation protection heroes, I guess you could say. He says that he developed the first count rate meter in the 1930s. We'll have to take his word for it. I couldn't find an earlier one. And very famous through the 1940s and 50s. And at one point, someone from the war effort, a general of some kind, came to him and was like, Dr. Evans, I need you to tell me a body burden for radium. And he was like, well, I can't really do that given the scientific uncertainty and the number of samples that we have. And he was like, no. It wasn't a question. It was a statement. You will do it, or I will draft you into the Army and I will force you to do it. And he said, Roger that, sir. And he got together with a few of his friends, including Harrison Martland here in the top right, who is a physician who is smoking in this picture. But being a medical examiner, he's also smoking around patients who are no longer living. So at least for his patients, it's fine. But they gathered together and they're like, well, we have these 8 cases. What do we think? What level of radioactivity will we be comfortable with our wives and daughters having in their body? They came up with 0.1 microcurie, and that was how they came up with the permissible body burden for radium, and that has largely stuck. So that's a fun fact about Robley Evans. Bottom left, also, I just want to recognize the dial painters themselves. As was mentioned earlier, many of them did suffer because of this exposure. And although this study is so interesting and so fun, we have to acknowledge that there is some suffering behind it. And then there were lots of women who also had very low exposures and that were willing to come to MIT or to Argonne to have measurements, to have whole body counts multiple times in the service of learning for the future and hoping that something like this didn't happen again. I also want to acknowledge my primary team who's working on this project, Kaylee Samuels and Rich Leggett there on the right at Oak Ridge National Lab. Some of you may know Rich. He has recently retired after 45.3 years at the lab. So well-deserved retirement. And then Kaylee is the lead million-person study point of contact at Oak Ridge, and they do the biokinetic modeling. So they model where radium and its progeny move through the body. My colleague who co-authored this particular presentation with me, Derek Yokish, is also joint faculty at the lab and also a professor at Francis Marion University. He does the energy deposition modeling. So he's the lead author on the recent ICRP publication on the pediatric specific absorbed fraction. And he also chairs a scientific committee that's looking at these updated dosimetric methods for dose to radium exposure. And here's how I describe myself: lead sleuth. So I do a lot of digging through the records to figure out what the scientists did in 1930. That's not the easiest thing to come across. Some of the old timers, it may be old news, but it's new news to me. I do modeling and QA support for the rest of the team, and I have aspiring lore keeper. Normally that's to make sure that canon stays straight in fiction, but there are so many good stories about the radium dial painters, about the scientists at this time that I never heard in school. And I want to try to bring those forward and recognize the stories and the importance of stories as well. So who are the dial painters? We heard about that. Radium was being marketed as a medicinal cure-all. So scientists, when they discovered radium, someone kept it in their pocket. They noticed it burned their skin and they were like, "Oh, Pierre, look at this. If I hold this radium against my skin, it burns it. Isn't that cool?" And he was like, "Yes, it is cool. I'm going to do it to my arm and I'm going to trace it and figure out how it works. This is amazing." And well, if it burns skin, maybe it also burns skin cancer. And it does. If it's good for cancer, it's expensive. It's good for everything. So this is kind of how it led to this idea of being a medicinal cure-all. They also recognized in the early 1900s it could be combined with phosphorescent material. William Hammer is probably the person to discover that. And in his lecture, when he's talking about these different radionuclides, he holds up a vial of it. And he's so excited about, the mysteries of the universe. And maybe this is going to be a source of light in the future. It doesn't require any energy input. So this is how really excited about this that they were at the time. Thousands of workers, though, most of them women, and I'll show you a figure that kind of breaks it down by sex, using the lips to finely point the brushes to paint delicate pieces quickly and precisely. So anyone here sew? Has anyone here threaded a needle before? Okay, better. So if your thread gets frayed at the end, you lick it, maybe draw it against your teeth so it's nice and pointy, and then you can fit it through. That's what they were doing, but with paintbrushes. So they get that really fine point because you're painted by how many you did, and they also have a person on cleanup duty. So if you missed a number, they would go behind and clean up, but then that you didn't get paid as much for that. So that's one of the reasons that they were lip pointing like that. I also wanted to highlight this quote from Pierre Curie. I cannot read it from here, but he basically says, this is a really cool thing that we did. And I really hope we're mature enough to benefit from it, but I'm kind of worried that maybe we're not going to make some of the best decisions. And so that's kind of foreshadows, I think, what happens with radium and the dial painters. Another thing to point out, that's an original ad there on the right. I looked that up in a library. It says girls wanted. And it really was in many cases girls. How old do you think in the data that we have the youngest dial painter was? How old? I heard 14. I heard 10. Any other guesses? 12. I should have brought a prize. I could get more answers that way. It was 11. 11 years old. Imagine 11-year-old painting with radium, licking the brush, right? So in many cases, they were girls and young women. So this is more cool, I think. It's speaking of historical significance. Top left, you see the woman painting, and in behind you see some like tubey things. That's going to be like varnish that she mixes with the paint. And Massachusetts Institute of Technology was moving their museum from building A to building B. When they did that, they found some Robley Evans stuff that he had collected. Super cool. So I got to hold in my hot little hand a tube that a radium dial painter had painted with, which was really exciting. I basically made friends with this woman, Dr. Florencia Perry. Her undergraduate degree is in biology, and then I think history of science or art history is her PhD. And she well recognized the historical significance of this, as did health and safety. Right. So there was some really high activity stuff that they had to get rid of. But this is still pretty radioactive, but they retained it because of the historical significance. For me as a dosimetrist, I was particularly interested in the size of the crucibles if we're going to do external radiation exposure, to know the geometry of that. They were a lot thinner than I anticipated. That paint, y'all, is not still glowing. That I have brought a UV light with me. So that's so I could see where the paint actually was. I know it's not just the zinc sulfide though, because also I obviously brought a radiation detector with me, which you can see there to the right. So to give you an idea of the magnitude of the painting, 1913, 2,000 watches and clocks illuminated by radium were manufactured in the US. A few years later, 1920, 4 million of these watches were made in the United States and 1 million of these were exported. So maybe some of your dials were painted by American dial painters. Totally possible. Also, just to kind of give you an idea of where culture was in the United States in 1920, that's when the 19th Amendment, giving women the right to vote, was ratified in the United States. So that also kind of explains why we're like, meh, women are painting dials. Oh, well. In 1921, von Saucicki, another fun story, he developed the initial paint used, the formulation used in the United States. In this article, he talks about, you know what, one time I almost dropped radium, but it's so precious to me. I held on to it even though I knew it would hurt me. And basically it burned me down to the bone, but that's fine because that's the sacrifice that science is willing to make. Also to give you an idea of the lack of safety culture at the time. He died associated with his exposure eventually. All right, here are some dial painters. On the left, Charlotte Purcell. These are both from Illinois. There were two major lawsuits, one on the East Coast and then this one later on in 1938. And you can see them both demonstrating lip pointing. On the left, Charlotte, you see that she is missing her left arm. It had to be amputated because of the cancer growing there. She eventually, she lived to her 80s, but she did eventually have to wear a back brace because her spine was basically collapsing. And on the right is Catherine Donahue. She's in bed, and that's her lawyer, the girl's lawyer next to her. She was sub 100 pounds at this time, which is what, 45 kilograms, less than that, just a tiny thing, two small children. And they had to have the deposition here because she was too weak to go to the courthouse. And unfortunately, she did pass away shortly thereafter. But the women did win this lawsuit. To give you an idea of what the intakes were like, this was originally in microcuries, but because I love you all so much, I converted it to becquerels. So a couple of things to take away from this. Notice the far column on the left, less than 18. Notice how many data points are sub 18. So this really is girls and young women. The red dashed line, that's when they banned lip pointing. They finally figured out, oh no, people are getting sick because of the radium, right? So that's when they said stop lip pointing. And then that gradually over a couple of years, people did stop lip pointing. But then you can see that there is a couple orders magnitude drop off in the exposures once lip pointing was banned. So this is an interesting study for the epidemiologist because you have a wide range of doses associated with this exposure. Female is the purple X's and male is the green circles. In general, though, the males tended to be like young men, like carrying trays from one place to another and typically didn't paint themselves. They may have also like transported paint vials and things like that. There's a gap for a little while because people are like, whoa, this is a really bad situation. And then it picks up again in the 40s with the war effort, when again, there's that need for the military dials that you can see all the time, even without power. Weren't there dial painters in the UK? You might be asking. There were. Here are some pictures of some. Look at how nice the health and safety is. You have the ventilation in the middle there, and you have the cap to keep dust from the hair, and you have the leaded glass as a shield. This is the earliest paper that I personally could find about the British luminizers. They don't talk about any earlier in this particular paper. There may be probably are some folks here who know more about those women than me. But what I did think funny about this paper was they were talking about the likelihood of exceeding the workplace standard at the time. And they were like, it's really unlikely, except, and they list a couple of things. And the last one they say is slovenly work practices. And I'm just wondering if that's throwing shade at the Americans or if that's very genuine. But there were dial painters in the UK. All right, I mentioned the last follow-up was in the 90s, and the work that we're doing on the dosimetry side is to eventually support the epidemiology. So we're looking at annualized organ doses to provide to the epidemiologists to look at risk. It's been tons of progress since the 1990s scientifically. Most of the dial painters, I think there's 7 maybe still left alive, but they could perhaps be children of dial painters. So there's the opportunity for the life study over the lifespan as well. We're approaching this in kind of a twofold, what we're calling person-centered approach. The first one is, you may have guessed from my telling you why that I think stories are very important, is this recognition and incorporation of prior personal experience and scientific accomplishments. There's a lot of information that we can gain just by talking with people. There is a very nice library in Ottawa, Illinois, where those dial painters are that we visited. We've talked to the librarians there. We talked to someone's great niece who was a dial painter, and to get those stories that can really inform what we know about what was happening at the time, and also looking at some of those primary sources. So that's like the story community knowledge and what our prior scientists actually did, because sometimes that's hard to dig up. And then again, incorporating this kind of modern dosimetric approach. So this individualized dose determination as practical and possible, because that's the epidemiologist's dream. Individual measurements of the women at multiple time points following chronic intake of radium. So that's going to give us a better statistics associated with the intake, applying reference models to an individual's age at exposure and length of exposure prior. They used adults, but as you saw, lots of people weren't adults. And so the teenage model may be more appropriate. Improvements to age and sex dependent models, particularly for females, lifetime of workers, and then intake rate by workplace and workplace practice. One of the reasons we think about that is, so the prior epidemiologists made an association with bone cancers and head cancers. They also noticed some increase in other types of cancers, but they weren't able to make a definitive connection. So for example, they noticed an increase in breast cancer, but they couldn't associate it with anything. So we think that by linking to workplace and also things like natality, so how many children they had, they might be able to get at why there seems to be that excess of breast cancer. They also used radium-228 in some places, which has a shorter half-life, obviously a different decay chain. And so that's going to influence the dosimetry as well. And then there's some biodosimetry, there's some blood slides that we might be able to tie in as well. So to do that, we need the radionuclides, 226 and 228. The decay characteristics are well known. Activity in tissues as a function of time, that's going to be the biokinetic piece that we're updating, and then energy deposition in tissues of interest. That's eventually how we're going to get to what the epidemiologists want. Now, what do we have? These measurements. So it's super cool. I'm going to come back to this real quick. So you saw this before. So the top decay chain is radium-228. I guess that one's new. The bottom one is 226. So we start out with alpha decay. And then for that bismuth 214, that gold star, that's a meaningful photon emission. So for radium-228, you'll notice that the first alpha emitter isn't till a couple of progeny down the line. So they did have to leave it on the shelf for a little while to get that alpha emitter that they wanted. But it was very cheap. And because of that short half-life, it had this, what they call the greater practical luminosity. Okay, but that meaningful gamma, that's what I wanted to point out to you. Early on, very early on, Elizabeth Hughes, as you saw, did some of these measurements. They basically said, here's a scintillation screen, blow on it. Did it sparkle? Yes, you're contaminated. No, you're not contaminated. That's basically what they had at the time. And they improved from there. So eventually they had the technology to get at what the body burden was. Because the first decay product is radon. So some of the radium might decay to radon, and you might exhale that. Or the radon could decay in the body, and then you don't exhale it, right? So you kind of need what was exhaled and what wasn't exhaled to really get at the intake and thus the dose. And so they did that. They measured both the exhaled radon, and they did basically gamma spec to measure what was retained. So they had an emanating fraction and a retained fraction, which is pretty cool. And you can see pictures of that at the top. And they would sometimes even mail these globes to people and just have them send it back. And then the meter arc method is classic. You literally laid like a banana. So each part of your body would be 1 meter from the counter. And you did forwards and backwards, right? Because of the self-shielding of the body. All right, differences between then and now. On the left, we have the radium 226 and 228. This is the absorbed dose rate to bone and dosium, just to kind of give you an idea of the difference between the isotopes. But this is log-log, so it's a little bit misleading. Radium 228 with the shorter half-life deposits energy over a shorter amount of time than that radium 226. And then on the right, that dashed purple line, that's the 15-year-old, and the black line is the adult. So an order of magnitude, again, that's log-log, so an order of magnitude difference. So here's the case study I promised to show you. Notice when they only had one measurement, they had to make an assumption about the emanating fraction. And then later on, they were able to take both measurements. Here's what that looked like. So we basically fit a curve to that. We assume chronic intake over the time, and then this particular person stopped lip pointing in 1926. So we reduced that intake rate by an order of magnitude. And then we're also able to get organ doses from that. And this is just illustrative. We would do this for basically everyone that we have measurements for. And to compare that to what Argon did, Derek determines that the ingestion rate is about 10.7 kilobecquerels per day for a total ingestion of 11.6 megabecquerels, where the previous estimates by Argon, 50 megabecquerel. So it's a big difference. And the reason being largely is to the difference in age is ultimately what we've determined. Just given the time, I want to highlight also this idea of so what I previously showed you was age specific for the energy deposition, but not for the biokinetic model. They're also working on doing an age specific biokinetic model. And this is just a sneak peek. I made a little joke because there's a peek there. Using multiple measurements and information we have, this is again, a big difference between that kind of orange, red, and blue line doing the age and sex specificity in the biokinetic model, which we will be incorporating later on. And of course, doing the annualized doses. To summarize, this cohort is unique in the million-person study. It has by far the most women. And it is associated with high LET emissions and internal, which a lot of our cohorts have that external exposure. We can estimate annual organ doses using the latest models, potential additional benefits for other applications like radium-223 used for prostate cancer therapy, occupational environmental exposures. And then this is a picture of one of the very last remaining dial painters at the dedication of the statue in Illinois. Thank you.
Thank you, Nicole. We've now got about 15 minutes for questions and a little bit of discussion. We've had a couple of questions come through, so over to you to ask those.
Yep, so we'll start with the ones in the app. So for Karishma, is the UV resin for sealant something you've developed yourselves, or is it an existing product?
So this is an existing. So this is an existing product that we use. We get it from a acrylics supplier through our corporate procurement route. It's actually originally designed for use for like glass-to-glass bonding. So the way we actually learned about it was museums used it to create display cases, and then we did some of our own testing to sort of see if it would be suitable for what we wanted to do, because it's quite good in that it's like a thick gel, and effectively you cure it with a UV light, and then it's like a hard plastic resin. So that's something that we externally source.
Cool. For Nicole, What impact do you think individual stories from the radium dial painters have on the discussion on the consideration of detriment in radiation protection?
On the consideration of detriment.
Yeah.
I think that the stories of the radium dial painters, people are, I don't want to say persuaded, but stories have an impact on people. They tend to get people to listen and help. Again, level the playing field's not the right word, but it helps people find common ground and kind of come to a common understanding. So I think that the stories of the dial painters help us develop empathy with people, at least for me personally, coming from like just thinking about purely technical and like realizing, oh, this is real people and it's going to have impact on real people. And I don't know how that is related to necessarily the concept of detriment, unless we're talking about like DALYs and QALYs, quality of life adjusted. I think it could maybe support that. But otherwise, I think it just helps humanize the science.
Cool, thank you very much. Again, for Karishma, have you had any correspondence with the EA on whether the dials with resin applied could be held under the small sealed source exemption if the activity was sufficiently low?
So I think with this, my colleague in the audience actually does deal with a lot of our EA related issues, but I think as long as, because it would meet the definition of a sealed source when we seal it, so as long as it's below the activity limits for exemption, I don't see why it wouldn't.
Cool. Thank you. So we'll go to the room now. Please remember to wait for a microphone. We've got some radio mics about before asking a question. Are there any questions in the room?
Karishma, what was the gamma dose rate sitting inside a Sherman tank?
Off the top of my head, I'm not sure. I'd have to get back to you on that one, but I think it would depend on how many dials that they had.
Any other questions in the room? Down at the front here? Oh, sorry. Was this one over here?
Behind you. Just a question for Nicole related to the detriment question. I wonder whether you were able to estimate the fatal cancer risk at all from the intake of radium and to come up with a figure, and did it look anything like 5% perceive it?
Great question. The short answer is no, because we have to do the dosimetry first before the epidemiologist can get a hold of it. However, radium is really interesting because at least what the scientists found in 1990, that 0.1 microcurie was a good number for body burden, because there were for both 226 and 228 certain body burdens that they did not see any cancers below.
Thank you.
Yeah.
One over on the front there.
Thank you.
Yeah, another question for Nicole. Is that on? Oh, yeah. You talked about exhaled radon. I didn't quite get it in the presentation, but what was the actual rates of emanating fraction and retained fraction?
So I'm sorry, can you repeat your question?
Yeah. So you talk about exhaled radon.
Yes.
What was the actual emanating fraction and retained fractions?
Oh, the emanating and retained is basically, so there's, let's say 100% of radium, right? And so as it decays, some of that radium that's decayed to radon is exhaled. So that's like, I don't know, 30 to 70%. And then some of it is retained. So they're basically fractionating how much of the total radium in the body made it out through radon versus how much then stayed in because the radon decayed in the body.
Any further questions in the room? No, cool. I'll go back to the. Oh, sorry.
One more.
Didn't spot you.
Cheers. Again, it's a question for Karishma. With the gel, when it's applied and cured, can it then be removed without damaging the items, given the historical significance, if needs be?
So no, so with this, we assume that the seal is permanent. So, and that's kind of the reason we apply it, because in that way it's sort of effectively removing that risk of contamination because it's a permanent seal over it. Obviously, this is something that we do let our customers know in advance because, you know, as I said, we've still not got that data to build up a picture in terms of the long-term effects and what happens over the exposure to radiation over time. But this is something that we do let them know, and then it's sort of up to them to decide if they're willing to accept that and go forward with it.
So from the app for Zori, about radon monitors, could you suggest any suitable monitors, active or passive, for Foron?
For Toron.
Yeah.
There is a double detector which claim to measure Toron, and I'm not so sure about. There is an ISO standard which UK voted against. The reason for this is because one of the detector said that the entry rate is smaller than the other, but doesn't give any numbers. So you can use open detector, closed detector, for example, if you'd like, but there isn't anything on the market that I know about. There are also some active instruments for measuring Toron, but the problem with Toron is 56 seconds is decay time. It is very difficult to measure it unless you just put your detector on the top of the Toron source. We already demonstrated that it is very, very difficult to measure. In PTB years ago, they had a Toron calibration, which was a small vessel, and on the top of the Toron source was that they put some instrument just to measure. So as I said, it's not easy.
Sorry.
I have a question. Do you have a favorite radon monitor? Are you allowed to have favorites?
No. Yeah, we don't. What we did was just to be obviously absolutely neutral to everything. Each instrument has good points, maybe not so good points, depends on what is the purpose of usage. But as I said, the most important conclusion is just these instruments need to be maintained, calibrated. Otherwise, I don't have anything favored. We had some problems with some of them, but I cannot discuss this.
Thank you. For Karishma again, when it comes to your seal and your dials, have you studied the properties of the gel in regards to effects of the environment and radiation on the opacity of the dial?
No, so that's one of our sort of key areas to look at going forward in terms of monitoring the changes over time. So obviously we work closely with the curators of the museum. They will do their visual inspections. So far we've had some sources. I think the earliest ones were sealed at Fleet Air in 2022. So they're about 3 coming up to 4 years now. And we've not noticed anything, but again, we've sort of got good open communication with the curators, and they'll get in touch with us to let us know if they do notice anything unusual about the seal. We do have some plans in terms of cross collaboration across wider AWE, and we've got some colleagues that have experience with looking at radiolytic effects of acrylic. So we've got plans in the work for the next phase of the investigation to sort of do some internal testing of the acrylic ourselves. So hopefully we should be able to get more information on that.
Nice. I have a similar follow-up question. Did you study the aging of the gel?
So no, so again, I think that's something that we'd probably look at in terms of ongoing research to see sort of over time, because this is effectively our original data set are these items that we've sealed originally. We've not really got, they are our test pieces for all effects and purposes. So it's just a case of keeping an eye on them and monitoring them over time to see if we can see any changes.
Okay. Question for Zori. About a radon chamber, how quickly can you change the concentration in the chamber? How long would it take to change from the lowest concentration, 400 becquerels per meter squared, to the highest? They've got 8,000.
Well, it is my colleague Chris that is more experienced in doing this. The chamber can be vented, and of course we're paying for the charge of radon. Yeah, it can be done. We don't. I don't see why we need to change so fast. It is not required. But we can change it. And we did very, very good experiments for other people for research purposes. There is a good publication about about the range of concentration that you can do. So for 8,000, for example, what you need to do just to open all 4 radium sources, close to the chamber, and leave it for about a few days, and then you can reach this concentration. And with radon, it is good to have stable concentration, but also when you'd like to go to 300, obviously one of the sources will be only open. First, the chamber will be vented, then you open the sources, and then you keep it obviously as low as possible. So it is not about fast. Radon is not a fast thing. It is it is there, but we know what we're doing, and we can also change the equilibrium factor, which is also interesting. We have monitoring equipment of equilibrium factor, and we know how to do it. So yes, it's possible. Fast, I don't know, cannot say. But if you have any questions, just email me, and I'll obviously contact my colleague, and he will be in contact with you.
Cool. So we've got one more for Karishma. How do you apply the resin to the open source radium, and are there any issues with contaminating the applicator?
Okay, so for this, it comes in sort of like a bottle with a plastic nozzle, and we just effectively apply it directly from the bottle. It's quite a thick, viscous gel, so it kind of like holds its own shape, and that way we can sort of apply it directly to the item without actually having to make contact with the item. We obviously don't want to use any sort of like paintbrushes or anything like that, because then you're dealing with generation of contaminated waste, which is something that we want to avoid. So it's literally just straight from the bottle. And then that avoids, creating any waste.
Nice one. Is there one more in the room over there?
This is just a question about instrument calibration and capacity. So if there's all these companies now, with all these instruments, have we got enough capacity to be able to do the calibrations, or is there a risk there that they'll all flood the market and then not be able to get calibrated?
Yes, we have capacity because the chamber is quite big. We can place a lot of instruments there. As I said, the calibration of these instruments is a little bit different to our normal calibration, which is 2 days in nitrogen, 2 days in the chamber, because the response time of these instruments and mostly is unknown. So we're doing 1 week in nitrogen, 1 week in the chamber. As I said, we have capacity. Well, we need more staff, as probably all of you need more staff. With current restrictions, we're a government organization, but yes, if you approach us, we will discuss, and I'm sure that we'll be able to provide the calibration meaningful time.
Okay, thanks everyone. I'm going to bring this session to a close, but in terms of that question, it's supply and demand. Someone will provide a service if there's a demand for it. So, so can you please thank our speakers first of all? Secondly, just a very quick reminder, Best Exhibitor Award, final votes by 13:20 this afternoon, and the annual dinner. If you don't have a table, you might miss out on a seat, so make sure you've got one. But if you don't want to go, please let the organisers know so they can allocate it to someone else. And thank you all for your attendance.